Hey Jack, here's your 12.3 to 12.5 lesson. So you can go ahead and do your homework and keep up and then send me your test when you're ready to do that. I'm going to upload two videos. This one that is first lesson you're missing and the last one that you just missed that I just finished with Maddie. So without further ado, let's go in. 12.3 surface area of pyramids and cones. If you remember when we did in class, the last time you were in class, we did surface area of prisms and cylinders. We're moving on to pyramids and cones now. I went ahead and drew a pyramid for you to the best of my abilities because when we deal with pyramids and cones, we're encountering a new term. So that's very important to know. Again, a pyramid has a base. That base can be any shape. In my case, I put it as a square, but that can be a triangle, it can be a square, it can be anything you can think of. It has to be a regular polygon, so it can be a hexagon that's regular, whatever. And then it has the lateral faces. In my case, it has four because the base is a square with four sides. Then it has the lateral edges, and then it has the base edges, so basically all edges, and it has a vertex on the top. Here's where it becomes different. We have been used to use the word height, and that is the segment that starts in the vertex and drops to the middle and makes a 90-degree angle. That's still a height. But when it comes to pyramids and cones, we're encountering a new term, slant height. And that is the height that it's going to be valid for each of the faces of the pyramid. It starts in the vertex, it comes down on one of the lateral edges, and it forms a 90-degree angle. Why is that important? Because as we're going to go on to formulas, you're going to notice that instead of H, we're now using, I should have put this in here, this is called L, or that's the notation for it, where the height has always been H, right? But let's see first, we're on page 735. The first thing that you're going to have even as homework is problems like this, where they give you the height and they give you the side, but they want you to find the slant height. It really comes down to a Pythagorean theorem problem. Let's look at example one. You have a pyramid. Here's what we know. The side of that pyramid is 300. We know that the height of the pyramid, the height, not the slant height, is 321. I'm going to go ahead and erase all of these so we don't get confused. They're looking for L. What is the slant height? If you look at this, if I could just unite this place with this place, I am getting a right triangle, am I not? I can actually redraw it right here for you. And here's what I know. I know this is 321. I know this is L, no clue what that is. But I do know what this other side is because it's half of the whole side. Whenever the height comes down, it splits the segment it touches in half. That's 300. This is 300. That's 300. This is a square. So then that half is going to be 150. Now I can go ahead and go, oh, this is a right triangle. Okay, what are my legs? 321 and 150, which means my hypotenuse is L. I can go 321 squared plus 150 squared equals L squared. I obviously do not know what that is. 321 squared plus 150 squared is 1, 2, 5, 5, 4, 1 equals L squared. I'm going to take the square root. This is the last step you're going to take. My L becomes 354.3. 354.3 is my L. So when you solve problems like this, it's always going to be a matter of getting the right triangle, using the Pythagorean theorem, and solve for the missing part. And all the time, not generally, all the time, the slant is going to be your hypotenuse, right? So that's kind of the type of problems you're going to run into when you do looking for a slant area. Then we're going to move on to the next page, 736, and we're actually going to talk about surface area of a pyramid, which I already wrote it down on the board for you right there. It is the area of a base. Remember the B, the capitalized B stands for the area of the base, plus 1/2 times the perimeter of the base of the pyramid times L, the slant height. This is where that L is so important because you're not timing it by the height, but you're timing it by the slant height. And we're going to jump directly in example 2 because we need it really bad. Example 2 says finding the surface area of a pyramid. And that pyramid has a base that is a regular hexagon. We already know that. It tells us that. Here's what I know. I know the side is 6. I know that if I make the pyramid, I probably should draw it first before I do anything else. The other thing that I do know is that that slant height right here is 8. And I also know that if I would have to deal with this triangle, the apothem for this little thing is 3 square root of 3. This apothem right here. Why does that matter? Because your base, unfortunately, is not a square and it's not a triangle, a right triangle. It is a hexagon. So while I can very easily get my L out, they gave it to me, is 8. And I can also get my perimeter out really easy. One side is 6 times 6, my perimeter is 36. I need the area of that hexagon, right? For the area of this hexagon from chapter 11, it's going to be half times my apothem times the perimeter of this hexagon, right? That's where we are. So if I'm going to get to do that, this becomes half times 3 square root of 3 times 36. 2 and 36, 18. This is 54 square root of 3. My B is 54 square root of 3. I have my L, I have my P, I have my B. My surface area is going to become 54 square root of 3 plus half times 8 times 36. And other than doing this, I'm really going to use a calculator because, yeah, 54 square root of 3 plus 4 times 36, 237.53. 237.53 is my surface area. Is the book saying the same thing? Yes, it is. Praise the Lord. Actually, they went only with 5 because they're never consistent on their decimals. So, one of the things you're going to run into as you're going to work homework in this particular situation is they're going to give you pyramids. They're going to say the base of that pyramid is a regular polygon. So when you deal with a regular polygon, and we'll deal with it in a little bit, you'll see how we get there in the next subchapter, I think, when we do volumes. Always remember that a regular hexagon splits in equilateral triangles, okay? But we'll touch that when we get there. As we move to goal 2 on the next page, 737, we're moving into cones. Cones are a lot easier to work with because the base of a cone can only be one thing, and that is a circle. So circles are great. So basically, we take the area of a pyramid and we rewrite it using a circle. Instead of the area of a base, I can put pi r squared. That's the area of a circle. Half times the circumference just gives me pi r, because circumference is 2 pi r times half, that goes away, and times my slant height. Other than that, same formula. So you're going to find 2 types of problems in your homework. Either they give you everything you need and you need your surface area out, or they give you the surface area and you need to find either the radius or the slant height. They're asking for one of the 2. Let's look at this type of problems. Example 3 says this. Find the surface area of the right cone. Let me go ahead and draw the cone. This is our cone. A cone has a radius and it has a slant height. This is your L. It also has a height that we're going to use in the next lesson when we learn volumes. But for now, this is what we care about, that L, okay? And here's what they tell us in here. My L is 6 in example 3, and my radius is 4. Find the surface area. SA is going to be pi times 4 squared. That's my radius. Plus pi times 4 times 6. This is 16 pi plus 24 pi, which is 40 pi. You can either leave it right here, and I'm more than pleased to take this answer, or you can take it one more step, which is 125.7. I couldn't care less. I'll take either of the answers. So if you just go, this is easier to do pi, just do the pi's. If you want to plug it all in that online calculator that I sent the link to you, put it all in and give me this answer. I'll take either one of the 2 answers. And this is about it. That was 12.3. What we're going to do now is, because I need to know that you know what you're doing, I'm going to have you in a second pause the video, and I need you to work for me problems 8 through 12, all of them. 8 through 12 all. So here's how this is going to go. I mean, you've had a video before. I'm gonna let you pause. When you are done, restart the video, work them out, please. Make sure you get the right answers. It's very important. Then restart the video, and you're gonna have all of the answers on the board, and you can check and see if you went anywhere wrong, and why you went wrong. Okay, so pause and restart. Okay, here's all of your answers. In case you got confused about 10, I forgot to mention that. Remember we said this is the area of the base? That's the lateral area they're looking for. So really what they were looking for is pi times r times L. So if by any chance you miss this one out, it doesn't really matter, because if you have the slant height and then you have the radius, you can do 11 without doing 10 very easily. You can just plug it in there. But this is what 10 was. The lateral area is just that second part, just the round of the conus without the base. Basically, we're adding the base, which is a circle, plus that little cone that we're putting on it. Okay. And then on 12, they kind of gave you everything you needed. All you had to do is plug it in and get 24. Pause it if you need to, make sure all the answers are right, and then we're going to move on to 12.4, and we're moving into volumes. Okay. And we're going to deal for the rest of today with the volumes on all of these solids that we talked about. We're going to deal with 12.4. It's going to be volumes of prisms and cylinders. And then the next lesson is going to be volumes of pyramid and cone, and then we're done. Okay, let's deal about volumes. First of all, the volume of a cube. A cube is made out of just squares, and if you think about a volume of just a prism, that's going to be a rectangular thing, like a book or anything else. To find the volumes, we're going to do length times width times height, right? But that has to have a base that's a quadrilateral, otherwise it doesn't work. But for a cube, the volume of a cube is going to be the side to the third power. Why? Because if it's made out of squares, and if I'm going to be drawing this cube to the best of my abilities, this is S, this is S, and this is S. It's made out of squares, so everything is equal, which means you have S times S times S, or the side to the third power. It's the easiest formula for a volume that you're going to find. On page 743, that's where we are. Okay, it did it. We have three postulates. One of them is the volume of a cube. The other one is telling you that if two solids, polyhedrous, are congruent, then they have the same volume. So just so you know, in case that two things have the same volume, they're congruent. And then it says also that the volume of a solid is made out of different solids that you can add those volumes together. Example one is the one that really touches this. It says the box that we have over there, I'm going to draw it really fast. Again, I'm not the best drawer, but by now you know that. It says that it has a length of 5, a width of 3, and a height of 4. And it says here, how many unit cubes will fit in the box? What is the volume of the box? We'll do the volume first because that's easy. The volume is going to be the length, which is 5, times the width, which is 3, times the height, which is 4. This is 15 times 4, or 60 cubic units. You have 60 cubic units. That's the volume. Then it says how many unit cubes will fit there. Well, if the volume is 60 cubic units, that means 60 cubes will go in there. And the cube unit is made out of little cubes like this, that everything is 1. The length is 1, the width is 1, and the height is 1. So really, in 60 cubic units, we're going to get 60 unit cubes. So this is kind of how it works. You add them up. The way they did it, just to do this again, although I just erased it. Yay. Here it goes. Here's what they did. This is 5, this is 3, which means if I'll be to put cubes in there, I can fit 5 in 3 rows. That's 15 of them. And I can do 4 rows up. So that would be 60 again. And then we're going to move on to the next formulas that we're going to run into. We're going to skip the Cavalieri principle because you don't necessarily going to use it, but here's what it says. We're going to mention it because it's here. It says if two solids have the same height and the same cross-sectional areas, then they have the same volume, okay? So if they have the same exact height and the same cross-sectional area, whatever you cross-section it, the area is the same, then they have the same volume. Then we're going to move on to the volume of the prism. For a prism, the volume is really easy, is B, which stands for the area of a base, because remember, a prism can have a base that's a square or rectangle, which would be great. It can also be a hexagon, it can be a triangle, it can be anything else. And times we're going right back to your height. We're dealing with the height again, which is just that segment that unites two vertices. You know about that. And then the volume of a cylinder is the exact same thing, except a lot more specific. Why? Because the cylinder, the top and the bottom are a circle, right? So instead of putting the area of a base, I can for this one go pi times I squared times my height. I am very specific in this case. Let's look at problems that deal with prisms first. In example 2, it says find the volume of the right prism and the right cylinder. In 3, we have a triangular prism. This is what I was talking about when I said, you know, sometimes your base is not what you would think it is. And here's what we know. We know that this is 3. We know that this is 4. We know that the height is 2. But probably the most important piece of information is this right angle, which is put down here, but it moves up there too because the two triangles in a prism are congruent. Because if that is a right triangle, then the base or the area of my base is going to be half times my base times my height. It's a right triangle. Tricky problem in a second when you're going to learn not all of them are a right triangle. This could have been easily something else. But in this case, 2, my base is 6, so my volume is going to be 6, which is my base, times 2, which is my height, and that is 12. For part B, I have a cylinder, a lot easier life. Here it is. My radius is 8. My height is 6. My volume is going to be pi times 8 squared times 6, pi times 64 times 6, 384 pi. And if you leave it here, I'm perfectly fine. And if you want to take it one step further and tell me that it's 1206.4, I'll take it too. Either one of them will work, okay? Actually, this is 37. We always stay with 2 decimals. Let's keep at the 2 decimals. But I will take that there easily. If you just want to do the 64 times 6 pi, works for me just great. Now, when you deal with volumes, you're going to have 2 types of problems. One of them are just this straightforward. They give you everything you need. All you have to do is apply the formula and get the volume out. The other one is where they give you the volume and they're looking for one piece of information. Example 3 deals with that. It says use the measurement given to solve for x. You have a cube, which I already know it's made out of squares. And here's why they tell me that this is x and this is x and this is x. But they do tell me the volume of this cube is 100 cubed feet. Okay, let's write the volume of the cube. The volume of the cube is the side to the 3rd power. Let's replace what we know. The volume is 100. The side is x to the 3rd. We're going to take the cube root of it. You're going to use your online calculator for that because your other calculator won't do it. Oh, hold on. It's going to be 4.64. Again, when you deal with stuff like this, it's just plugging it in a calculator. In this case, they gave us the volume. They were just looking for the side that was missing. For the cylinder, for part B of this problem, they tell us that the height is 12, my radius is x, but I do know that my volume is 4561 meter cubed. Again, what is the volume of a cylinder? Pi times r squared times h. I'm going to replace everything that I know. My volume is 4561 equals pi times my radius is x squared times my height, which is 12. I'm solving for x, which means I'm going to divide by 12 pi in both places. I would say do it using parentheses. 4561 divided by parentheses 12 pi. I end up with 120.98. 121-ish equals x squared, which means x is about 11. Okay, round it up a little bit, but x is about 11. Again, two type of problems. Either all of the information is given, all you have to do is apply it, get the volume out, or you're going to have information given to you, the volume given to you, and they're looking either for the radius, for the side, for the height. One of them is going to be missing, okay? Now, let's go ahead and also deal with example 4. And then I'm going to do the same thing. I'm going to have you pause. Keep in mind example 4. Actually, no. I'm going to have you pause right now because example 4 is complicated and it's going to mess with you. I'm going to have you pause right now. Go to 746. All I need you to do is 7 and 9. I need you to do 7 and 9. Come back and let's check the answers. Pause it now. Okay, here we go. 7, and which is either 540 pi or 1696, or 9, which is 840. That's it. So if you need to pause, make sure you have the right numbers doing now. If not, we're going to go back one page just really fast, and we're going to go ahead and do example 4. That was a little bit too much information instead of doing the easy homework problems. In this case, it says using volumes in real life, and they talk about a cement block. You guys are just bought a house. This might, hit home. And they're wanting to know exactly what is the weight of one cement concrete block. And here's what it tells you. Concrete weighs 145 pounds per cubic foot. They want to know how much one single cement block is. If you look at that drawing, really, that is a prism. So we're looking for the volume is B plus times H, right? I have my height. I need my B, which is the area of the base. And if you look at that, and you know how cylinder blocks look, they're like a rectangular thing, but they have two rectangular holes in the middle. That's all look like that. So if I would have to find the area of that base, I'm going to need the area of the big rectangle minus 2 times the area of the small rectangles, right? Because I have 2 of them, they're holes, and they don't count. So the area of the big rectangle is 1.31 times 0.66. And then minus 2 times the area of the smaller ones, which is 0.33 times 0.39. Clearly, I'm not going to do this in any other way but doing this 2 times in the calculator, 0.33 times 0.39. I end up with 0.6072 or 0.61. This is the area of my base. I cannot continue this and finish it. The area of my base is 0.61 times my height, which is 0.66. And I don't know what that is. 0.61 times 0.66 gives me 0.40 cubic feet. Remember, 1 cubic foot weighs 145 pounds, which means 1 concrete block, sorry, I can't spell anymore. It's going to be 145 pounds times how many cubic feet do I have? Only 0.40, which gives me, I don't know what, about 58 pounds. In case you're wondering if you ever have to carry around a concrete block, it weighs about 58 pounds. And we are done with 12.4, and we're going to move on directly to 12.5 and finish this wonderful video. We're moving into volumes of cones and pyramids, and then we're done. So I am at 12.5 of pyramids and cones. For the rest of the class, this is where most of them had issues solving problems, and I'm going to touch base with you on that because it's important. The volume of a pyramid is going to be 1/3 times your B, which is the base, times your height, as usual, and the volume of your cone is the same as the volume of your pyramid, but now I know that my base is a triangle, Lordy, a circle. It's going to be 1/3 times pi times r squared times my height. Again, cone a lot easier because we know exactly what the base is. we're going to jump into problems. You're going to have two different type of problems. One, they give you everything you need, and then you find the volume. Two, they give you the volume, and you're going to have to find what's missing or one information. We're going to deal with example 1, finding the volume of a pyramid. And I need you to actually take your time and look at that drawing because this is very important. That pyramid has a base of a hexagon. And not only is that a hexagon, but it's a regular hexagon. How do I know that? I made it a lot taller than the book does. Here's how I know. If you look at it, each side has the same marking. Do you see that? That means that hexagon is a regular hexagon. Okay? Why is that important? Because in order to find this, I really need the volume, which is the 1/3 times the volume of the area of the base times my height. The area of the base is the area of the hexagon. And remember that we need the area of the hexagon, which would be normally 1/2 times the apothem times the perimeter, which is going to be really hard to work on. But if you remember that because this is a regular hexagon, everything is equal to each other, that means that if this side is 3, then this side is 3, and this side is 3. When we make that inside triangle, that is an equilateral triangle. And I have a formula in chapter 11 on the cheat sheet that you're allowed to use for your test that tells you that the area of an equilateral triangle is 1/4 times square root of 3 times the side to the second power. So really this becomes 1/4 times square root of 3 times 9, or 9 square root of 3/4. Now am I looking at this and you're going to go, well, that's great. We found the area of one triangle. I need the area of a hexagon. Well, remember, this is a regular hexagon. How many triangles are equilaterals do I have in here? 1, 2, 3, 4, 5, 6. So the area of that is going to be 6 times this number. And I got my area of base. There's 6 of these triangles in here. I find the area of one. I can times it by 6 and get the whole hexagon out. So this becomes 1/3 times 6 times 9 square root of 3/4 and times my height. And I think they gave me my height. This is 4. Let's see what we get. 4 goes with 4. 3 reduces with 6. I get a 2. This becomes 18 square root of 3. And you can leave it right there. Or you can go ahead and put it in, which is going to give you about 31.2. Either one will work. But you will have homework like this where it tells you that the base of each pyramid is a regular polygon. So as soon as you see 6 sides, you need to think hexagon, which means my initial triangle that I form is an equilateral triangle. I can find the area of that triangle by using that formula given in, I think it's 11.1 or 11 point something. Very fast. We get this area of the equilateral triangle. And then all I need to do is times that triangle by 6, and that gives me the area of the whole hexagon. And this is probably the most delicate problem you have. Also, you're going to have in homework problems that's going to tell you the same thing. Your base is a regular polygon, and that's a triangle. The only regular triangle is the equilateral triangle, which means as soon as you know that, they give you the side, you just apply that formula from chapter 11 and you have the area of a base without really having to work hard. When it comes to cones, life is a lot easier. Let's go ahead and move on to cones. And this is we're about to be done in a second. It says find the volume of each cone. On A, here's my cone. Boom. My radius is 12.4. My height is 17.7. They say this is A. What's the volume of this wonderful cone? Well, the volume is going to be volume of a cone 1/3 times pi times 12.4 squared times 17.7. And believe it or not, I am not going to work this by hand because I have not lost my mind. I'm going to do this 12.4 squared times 17.7 divided by 3, and I'm going to end up with 907.18 pi. You can leave it here. So all I did is I squared this, times it by this, and divide by that, left the pi in there. If not, you can go ahead and also times that by 3.14, and you're going to end up with 2848. Point mine is 56. The book is going to be a little bit different. It's 50 because they're using pi, not 3.14. So basically they say this is about this much. Okay. On part B, it's the exact same problem. Your cone is slanted, but it doesn't matter. The formula stays the same. You have a cone like this. It's kind of like this a little bit, but you still get the radius, which is 1.5. And they tell you the height